Welcome everybody. First of all, let me begin with thanking the organizers for arranging this wonderful conference and giving me this opportunity to present this work. So this work is essentially work done by my PhD student, so Deepak Gautam. And let me begin with a disclaimer that there is very little plasma physics in it, but we hope that this will be useful for plasma applications. So the title of my talk is Transformation Optics Inspired Finite Difference Field Solvers for Complex Geometries. And so this is the outline of my talk. So I'll begin with a brief overview of transformation optics, then how these ideas can be used for developing a Poisson solver, which potentially can model complicated geometries. Then we'll discuss benchmarking of algorithms and some of the applications that we have developed with the code. And finally, we'll give conclusions. So transformation optics is fairly, I mean, although it has picked up in last few decades, but the essential idea is quite old. The first idea that electromagnetism on a curved space can be mapped on a dielectric medium was given by Igor Tamm in 1924. So just about the time after general relativity was developed. Then the explicit equivalence between curved spacetime and anisotropic medium, the proof was given by Plebansky in 1960s. Then there was a period of sort of lull for a few decades, and then in around 1990s, John Pendry and his group actually give strong impetus to the field, and they basically formulated the invisible cloaking, and some experimental demonstration was done by Pendry and his group. Pendry, Schuring, and Smith. And independently, around same time in 2006, Ulf Leonhardt again developed the same idea from the conformal mapping point of perspective and showed invisibility cloak. In fact, Leonhardt has a beautiful review paper. When I was reading it, this idea struck me that we could use it for the computational physics. So what is the essential idea of transformation optics? So for example, if you have a space which is, assume that the space fabric is very regular, then you expect this ray, this light, the red arrow light is traveling in a straight path. Now, by some means, for example, if you distort the space fabric, then the same light would start appearing traveling on a curved path. That means the distortion of space has led to the path which is basically now getting, the light is getting curved on that path. But we know that light also takes the curved path when there is a dielectric medium placed in it. So the distortion in space can be equivalently mapped into a presence of a dielectric medium. And that is essentially a change in the refractivity index is sort of an equivalent to distortion in space. That is the essential idea of transformation optics. And the mathematical statement is essentially Maxwell's equations are form invariant. What do I mean by form invariant? That if you make a coordinate transformation from, let's say, x coordinate system to x prime coordinate system and calculate the associated Jacobian, then if I write Maxwell's equation in the original x coordinate system and then this arbitrary x prime coordinate system, the form is exactly identical. And I can go from these, provided that my quantities, for example, electric field, magnetic field, current density, charge density, and permittivity and permeability, they transformed in a specific way given by a Jacobian. And if you look into the differential geometry, essentially this is how a vector will get transformed. This is how a scalar with certain volume dependent will get transformed, and this is how a tensor will get transformed. So essentially the proof comes from a differential geometry. And we are not going to get into the proof, but the whole idea is the statement, the mathematical statement says that the Maxwell's equations are form invariant, and whatever is the coordinate transformation will do, I can absorb it into these modified permittivity and permeability tensor. So this is the essential idea behind the this form invariance and transformation matrix. So let me, to emphasize the idea, this idea, let us start with a very simple example where we assume a scaling transformation. That means the x prime is scaled by some factor s to x. So we are looking at x prime as s times x, where s is a number which is greater than, ideally it should be greater than 1, so that it's a stretching transformation. It should not be 0, it should be greater than 1. So if it's a stretching, so the space is getting stretched, okay? So if it's just a constant, we know the Jacobian will be simply an identity matrix with diagonals on S, and then you can compute this permittivity tensor, and if you put these things in this formula, you would find that if my primed coordinate system, that means the one which is stretched one, has a permittivity of epsilon naught, okay? In the unprimed, which is a uniform coordinate system, okay, the permittivity will be s times epsilon naught. Now s times epsilon naught, so s will play a role of a relative permittivity. So essentially when we talk about a dielectric or a parallel plate capacitor with a dielectric in between, the effect of a dielectric is exactly same as stretching the space. That is why the electric field goes down, and because if I could do the same electric field by increasing the distance between the parallel plate capacitors. Okay, so that is how the idea is. So if you could put a dielectric in between, essentially that is same as putting a stretched space. Okay, so this is the simplest idea one could think of. So how can we use this for our purpose, for example, in computational physics? Okay, there are many problems in physics in general and also in plasma physics specifically, where you need a non-Cartesian, non-orthogonal grid. For example, problems where you have flow through nozzle, flow over a sphere, or you may have a discharge where the electrodes are curved, or devices where the magnetic field lines are curved. So there are lots of problems where actually the field line is, the Cartesian is not a natural geometry. Okay, so generally we tend to solve these problems with more sophisticated finite element or finite volume codes. Finite difference is definitely not the preferred choice for this. But at the same time, we know that the first thing that we learn is finite difference. It is very easy to implement and do. So we would ideally like to have a simple finite difference code which could work with these geometries. So specifically, we are looking into now Poisson equation problem, because Poisson equation is one of the equation in electrodynamics. So this transformation idea of transformation optics will apply to it. So what the idea is then that we will map the problem on a uniform grid with a transformed permittivity tensor, so that we can solve a complex geometry or a non-orthogonal geometry on a simple orthogonal or Cartesian space. So that is the essential idea of this work. So as far as the Poisson equation is concerned, so let's assume that we have an unstructured grid over here, and we will represent it by prime coordinate system. I want to solve a Poisson equation here, okay? But I don't want to solve the problem on an unstructured grid. I want to solve it on a structured, nice, well-behaved grid, which I call it as a computational grid. So on a computational grid, instead of solving a Poisson equation, I'll have a generalized Poisson equation. So in the generalized Poisson equation, because phi is a scalar, it will remain as it is. It will not get transformed. But the epsilon and rho will get accordingly transformed. Okay? So that is the general idea. So what we will do is we'll try to find a mapping from computational domain to physical domain, compute these matrices, charge densities, and then solve it. Essentially, that's a very straightforward way once you know how to do this mapping. So a 2D formulation, I'm sorry, this is somehow getting distorted. The 2D formulation is basically, because we are going to solve a generalized Poisson equation, it takes this kind of a bit awkward form, but it is doable. Finite difference, so we can do it, how to solve it. We have these Jacobian matrices, and in 2D then you can explicitly compute these 4 components, epsilon xs, epsilon yy, and 2 diagonal components. So once these, and the advantage is once the mapping is fixed, these matrices are essentially pre-calculated. So you don't have to do it, every time this calculation, unless you are going to do an adaptive mesh where this has to be done every time. But otherwise, this can be pre-calculated. So another advantage of this method is now you can implement it on you can implement your multi-grid algorithm on this, because multi-grid, as we know, starts with an idea that you will work with a fine mesh, do few iterations of Jacobian or Gauss-Seidel on a fine mesh, then transfer its residue on a coarse mesh, then again do few iterations, because basically the main idea of multi-grid is high frequencies are eliminated on a fine grid and low frequencies are eliminated on a coarse grid. So, but essentially if I have to implement multi-grid again, I need a structured grid. If my grid is distorted, then again I cannot do the multi-grid algorithm. It's not that straightforward rather. So again, the advantage of going on this kind of a geometry is multi-grid is naturally implemented in this problem. Okay, so these are the 2 advantages. So you can construct a fast Poisson solver. Typically, another way of doing a fast Poisson solver is basically do FFT. But FFT again is not very suitable for unstructured grid. So now we have a solver which can do it on we can solve an unstructured grid problem by mapping it on a structured grid. So just to give you a few examples now, I'll just give a few examples of this idea. Practically, this is the idea. I'm more or less done. So I'll just give you how we can do. So we basically then took those equations, used finite difference, implemented multi-grid algorithm, and from scratch we wrote the entire code, and then so now we are just trying to show some examples. So some benchmarking problem. So we started with a simple problem that you have 2 coaxial cylinders. On an inner cylinder you put a potential boundary, other cylinder there's some Dirichlet boundary conditions on 2 edge. So how do you solve this semi-annular domain? You take a rectangular grid again and use this transformation mapping, which is x prime is simply x times cos y and y prime is x times sin y. So essentially for a constant x, if you square these two, you get x prime square plus y prime square is equal to x square. So it's a constant, the vertical line, constant x line, gets mapped into a circle. So you have this mapping. So based on this mapping, you construct these two permittivity components at each grid point. This has to be computed at each grid point, and off-diagonal terms are absent. Now, with these permittivity matrix, you solve this problem with this boundary condition. This is the exact solution with this for this problem, and if you look at the numerical solution, it matches exactly. We also did comparison of standard, if you had to solve this problem with a standard Poisson solver and against our solver. So this is a time comparison. The red one is a multi-grid solver, and the black one is the solver coming from the standard SOR or conjugate gradient, those kind of methods. So we can see as delta x reduces, the speed up increases. You get 100 times higher speed up, because multi-grid, because there is an overhead associated with this method because you're not solving exact Poisson equation. You're solving extended equation. So for large delta x, you don't get that much of a speed up. But as the speed up, as delta x becomes smaller, you start getting the advantage associated with this. And the error are actually scaling with, because this is a second order scheme. So we plotted, different norms, L infinity, L2, L1, and all of them are scaling exactly with delta x square. So you get a second order accuracy exactly. Okay, but the question you may ask is, do I have to have an analytical mapping only so that I can do it? No, I can actually generate a numerical grid and now construct my Jacobian by taking a finite difference on that numerical grid. So this is what we did. So we again found out how to generate a numerical grid. So this is where we have shown, this is my computational grid, and this is my physical grid, which is now a sphere, okay, or a circle. And how do you generate a numerical grid? Interestingly, you again have to solve a Laplace problem. So numerical grid, when you want to generate, you can think of it that your transform coordinates x prime and y prime are actually the harmonic functions of the original thing. So you solve again Laplace problem. And you just give whatever shape that you want as a boundary condition. So it is like a potential problem with potential given as a boundary condition. So whatever here, for example, if you look at this, the lower boundary on the computational domain is mapped into 1/4 of a circle, and then the all four. So this is how you construct a circle. So you generate a numerical grid again by solving Poisson equation for Laplace equation. So once you generate a numerical grid, you again do the same thing. You compute Jacobian, and then basically you solve this problem. So just to demonstrate that aspect, we generated a numerical grid, and this is my physical grid, okay? And on that, I put a boundary condition where phi is changing as some n times sine theta. So this is another well-known benchmark problem for Poisson solvers. So we took that problem, and then for this, you have an exact solution, and our exact solution, our numerical solution, which matches well with the exact solution. Again, if you see the time comparison, standard, you get a significant, because multigrid is helping us in developing that fast Poisson solver. And interestingly, when you look at the error analysis, again, even if the boundary is curved, the error is still scaling with second order accuracy. And if you look at similar type of, for similar problem, there is a JCP in 2020, they have used boundary element method, where these boundaries have to be mapped, and then from a rectangular grid, you have to do some interpolation and get those boundaries. So if you look at that method, the global error there matches with the second order accuracy, but the local error is between first and second order. So this is the advantage of this method, because we are actually doing implementation on a rectangular regular grid. The error is actually scaling with exactly second order accuracy and not in between. So this is an advantage. Now let us do few applications quickly. So one application that we thought is, many a times you want a very finer grid at the center of the domain, and as I move away, I want to have, grid is getting stretched so that the boundaries are staying away from my region of interest. So for that, you can use this function. So this is my computational grid, the first one. This is my physical grid. And just to demonstrate, I use the minimum delta x. We use this minimum delta x. And then on this stretch domain, take the complete uniform grid. Now, advantage clearly would mean that on a computational grid, my box size is only -3 to 3. Whereas if you see here, -14 to 14, because space is stretched. So number of grid points have gone significantly higher if I had done this calculation on a uniform grid spacing. So these are the permittivity tensors. And if you look at it, again, we give some Gaussian charge distribution. Now, because this is a Gaussian charge distribution, I have to map it, because rho will get mapped on because the differential volume element changes because of this mapping. I have to map rho into the computational grid. And if you see the speed up again, similar trend, as delta x becomes smaller, you start getting a significant speed up. Because otherwise there is an overhead of doing this unnecessary extra calculation of computing epsilon as a tensor, and also method will be useful when you really scale it to a small delta x. Then we did some few problems in fluid mechanics, like potential flow over a sphere. So you take a potential flow over a sphere. So this is where we use numerical grid generation. So this, you have a uniform grid everywhere, but only at a boundary here. Again, we give that straight line getting mapped into a circle. And then you solve a Laplace equation, generate this grid. Once this grid is generated, you map it, you compute a Jacobian, do everything. Then again, you get this permittivity tensor. And these are the streamlines, which are the standard result again. Although we took a problem from fluid mechanics, there's absolutely no reason we cannot use this for a electric field due to a charged sphere, for example. All I have to do is to change the boundary condition on the sphere, and then I would again generate an electric field due to sphere. And then again, just to extend this, what we did is you can make now more complicated shapes. For example, this is one of the complicated shape again. Just as a trial, we did it. And on this complicated shape, if you see, again, this is a flow over complicated geometry. There's absolutely no reason why I cannot do electrostatic problem with this. So that is the central idea. You make a transformation, go to a standard, nice, well-behaved grid, and then compute the field and then transform back to the original space. Okay, and this is my conclusion. So we have developed a robust Poisson solver for solving these complex geometries. Method is, at least I found it, method is very physically intuitive and incorporating these ideas from transformation optics. And it can be applied to large number of problems in physics, not just in plasma physics and fluid dynamics, because Poisson solvers are required everywhere. Even in fluid dynamics, you have to solve for incompressible flow, you have to solve pressure field equation, which is a Poisson equation again. So you have to, you would need, it could be applied there. And it provides exact second order accuracy for all, L2, L0, and L infinity and L1 norm. So global and local accuracies are exact second order. There is an additional overhead that we have to keep in mind. It will not blindly work if you have a smaller problem, maybe if it's a bigger problem. Another thing is, which I have not mentioned here, because this is a night structured grid, parallelizing becomes very easy again. So that is an advantage. Potentially this could be applied for an electromagnetic problem as well. And I have already written a Poisson, the Yi solver, which would work on this anisotropic medium. So you could actually solve light propagation on a complex geometry as well using this. And we are currently actively pursuing extension of this, incorporating this Poisson solver in particle in cell simulation, so that we can do more realistic PIC calculations with on a complex geometry. So with that, I'll thank you very much.
Thanks, Bhushan, for this innovative, the talk with innovative approach. I think it's very interesting, both for the scientists and the students. Yeah. So now we will receive some questions.
Hi, nice talk. I'm Jayakumar from IISc. So this sounds very similar to what you would do in a Boozer coordinate transformation in a typical PIC simulations, right? So it has similar connotations. But there, if there are singularities, for example, in your problem, if you were to solve this problem, a 2D problem on a sphere, then the grid would have a singularity. You can't build a sphere using just rectangular grids, right? So how would you tackle that problem?
Yeah, so there you would obviously have to have a three-dimensional 3D, you probably cannot map a 2D problem on a 3D unless what I have in mind is you use a Fourier decomposition, and then one of the dimension, it's like a pseudo-spectral, one of the dimension you Fourier expand, and then that itself is a mapping. So you work for those modes and then mapping on a 2D problem. For example, people have done axisymmetric, non-axisymmetric cylindrical problems on a 2D grid by expanding it on a Fourier mode, and then you map it on a 2D thing. So the computational cost for that is not n cube, it is basically number of modes multiplied by n square. So that is something one could explore. Yeah. But otherwise you'll have to do because it's otherwise point-to-point mapping, so you would have a 3D grid and then mapping on this. But still you have an advantage because 3D grid would be still structured. So that would be an advantage.
Hi sir, this is Yasir from IIT Delhi. So you told us that Maxwell's equations are form invariant, but what about the Lorentz force equation? Because if that's not form invariant, what would happen to the additional overhead during say a pick or some other calculation when you need to convert the velocity and the positions, etc. From this unstructured to the structured?
Yeah, that is what we are exploring. So as the easiest way for extending it to pick is you just transform the field part to this, do this, and then particles are anyway gridless. So you probably can live with that. We are exploring that whether we can transform the entire problem on entire pick problem on this regular grid. I still don't have a very clear answer on that. I'm not very sure about that.
Also the form invariance, is it also like relativistically unchanged, because in the relativistic limits?
Oh yeah. It's in fact in transformation optics people have actually found the optical analogs of event horizons and things like that. So that is very well done so that is not a problem. That is the beauty of Maxwell's equation, and that is why this is one of the most complete theory that we have.
Thank you.
Yeah, perhaps I got partially the answer what I was going to ask question while you were answering him. My point was basically, as you told, Maxwell's equations are form invariant by Lorentz transformation. But now in addition you have another kind of effective transformation due to your additional external effect. My worry is that maybe it is not an worry, but I'm just wondering, now in any case you are making the equations form invariant by changing, your epsilon, density and so on. Right. Now you are putting top of it Lorentz transformation. Together it will not violate.
It's the last part is not, so we can transform this, the last part is
suppose I am doing different way then. Maxwell's equations are, as you said, invariant under Lorentz transformation. Now, so you have in any case prime and unprime frame. Then you have additional effect coming due to your medium effect, I would say. Whether you are considering curve space, effective some effect or medium effect, whatever. And further you have to make a further transformation so that equations remain again invariant. So already we know Lorentz transformation will make it invariant. Further you have to change, as you said, electric field, magnetic field between two frames appropriately. Right. Now in addition you are saying due to medium effect, if I use the word, additional transformation have to be there so that again equations remain invariant.
So you mean the medium itself has an intrinsic effect?
Exactly. And that also have to be transformed and due to Lorentz transformation and in any case, as you said at the beginning, curve space time, which is actually not Lorentz invariant either. Right. Local coordinate, you have to be very careful. So that's my general worry.
I think we should still be able to do it because at the core of it, it is still the original is in the notations that I'm using. It's in the prime space, that variation that you're talking, and then I can still incorporate those variation itself in the prime space, and then entire transform. I can transform that problem with variations on the unprimed space. So I would imagine that we should be able to construct it.
So thanks Bhushan for this excellent talk.